Okay, students, today we are going to be talking about binary ionic compounds in chemical nomenclature. We're going to learn to write formulas for the compounds that are binary and ionic, and we're going to learn how to write their names as well. So here are some example problems that we'll be able to get through by the time you're done with this video. Here we have names and formulas for compounds, and you should be able to provide the opposite one. So here we have lithium nitride as the name, and you should be able to write the formula to go with that. Here we have the formula K2S, and you should be able to write the name for that compound. And here we have the name magnesium oxide, and you should be able to figure out the formula for that as well. So again, we're doing binary ionic compounds only in chemical nomenclature here. And again, there are two major types of compounds, and keeping them separate from each other in your mind is really important. There are ionic compounds, which are formed from a metal and a nonmetal, a metal ion and a nonmetal ion, and molecular compounds that are formed from two nonmetals. And again, pink ones are metals, blue ones are nonmetals. You should have easy access to a periodic table on your computer or on paper somewhere at your house. So make sure you've got that. So ionic compounds are made from atoms that gain or lose electrons to become charged ions. And we talked about this when we talked about bonding. In fact, I showed you this little animation that I made. Here's a sodium atom. It's got 11 electrons. And look here, we've got this one lonely valence electron all by itself. And it doesn't really want that outermost single valence electron. Well, okay, atoms don't really want things anyway. They don't have brains. But it would like to have, it would be best if it could have this full outer valence shell here and just get rid of this little electron. And sodium is going to bond in this case with fluorine. Fluorine has 9 electrons, 7 valence electrons. It would really kind of like an extra valence electron. It's got room for an extra one. And fluorine is very electronegative, so it'll pull electrons toward it. So here goes that electron, and there it is. And now they both have full outer valence shells, but they've gained or lost electrons. And of course, when that happens, that means you get a charge. If you lose an electron, your charge becomes positive. If you gain an electron, of course, it becomes negative. And so sodium lost its electron, so here's its +1 charge, and fluorine gained an electron, so here's its -1 charge. And now, because they have charges and opposites attract, they're attracted to each other, so they kind of stick together. And they both have their 8 valence electrons, so these are happy, stable atoms. And this is a happy, stable relationship. So this bond will be very stable, very strong, and it's very hard to break these two elements apart because they're charged and they stick together almost like magnets. The names for ionic compounds are really simple. You just put the name of the cation with the name of the anion. Cation, remember, is positive, anion is negative. So the names of the metal ions, the cations, are just the element name, unless it's a transition metal, and then you have to use a Roman numeral to indicate the charge. So if you recall, transition metals are that D block and F block elements in the middle of the periodic table. So Na plus is what we call the sodium ion, and Ca plus 2 is called the calcium ion, and Fe plus 3, well, iron's a transition metal. It can have different charges, and so we have to indicate the charge. So it's the iron 3 ion, and that's 3 as a Roman numeral, Roman numerals in parentheses there. The nonmetal names are also pretty easy. You just change the anion name from the element name to add an "ide" ending. So Cl-1 is called the chloride ion, and O-2 is the oxide ion, and N-3 is the nitride ion. There are some ions that end in "ate" or "ite", but those are only found in ternary ionic compounds, and that's not what we're doing today. We'll get into those in the next couple of days. You do need to be able to, for writing the formula, you need to be able to predict the charge of any ion that you might find. So here are some common charges for the ions. All of these group 1 elements tend to form +1 ions. Hydrogen occasionally will be -1. but everybody else is +1 all the time, always. So again, no need to indicate Roman numerals because the charge is always known. These guys, the alkaline earth metals, have +2 charge. These guys over here are +3. I skipped the transition metals, recall, because they're a little bit weird. Carbon's family is +4 or -4. This guy's getting in my way again. There we go. +4 or -4. Nitrogen's family is -3. Oxygen's family is -2. The halogens are -1. And of course, the noble gases are not going to form ions. So you do need to be able to predict the charges. This is something that you need to memorize. You should be able to look on the periodic table and know any of these elements that I covered with purple arrows. So again, you need to be able to tell me which charge any of these elements would form in any given situation. Now, this family here, carbon's family, we said it's +4 or -4, and it depends on who it's bonded with. If carbon is bonded with, say, calcium, which is +2, well, a +2 and a +4 would not attract, they would not bond together, so that's not going to happen. So if it's a +2, then you might have a -4. But if carbon is bonded with something negative, then it can be positive. And the last thing we're going to do here is practice writing some formulas. This is a little bit difficult. It takes a little bit of effort to get good at this. The best way to write formulas for binary ionic compounds is to make a table like this. You've got the name, you're going to write the cation and the anion, and then you're going to make the formula. And you have to make sure the charges are balanced. So we're going to start like this. Sodium chloride. If we looked on our periodic table for sodium, we'd find it's a group 1 element. It's got a +1 charge. So its cation looks like this, Na+, or +1. The anion, the chloride ion, is Cl with a -1 charge. And then we're going to ask ourselves, if I had one of each of those, would they balance out? Would that make a neutral compound? +1, -1, yes, it would balance. And of course, you know the formula for sodium chloride probably already. It is NaCl. One atom of each will make it neutral. The next one we have is sodium oxide. I did sodium 3 times in a row there, so we know this one is Na+1. Oxide, of course, is in the -2 column, so this is going to be O-2. Now, we need to know how many sodiums are going to have to be together with an oxygen to make it balanced. Each sodium has 1 positive charge, oxygen has a -2 charge, so we're going to have to balance those out by having 2 of the sodiums total to go with each oxygen. So Na2O is our formula on that one. Sodium phosphide, here's our sodium again. Phosphide, phosphorus, is in the -3 group on the periodic table. You can look it up if you're not sure. And so this one is a little tricky. We're going to have a lot of sodium to balance out 1 phosphorus because it's got a -3 charge. We're going to have 3 sodiums. So Na3P is the answer here. And then the last one is calcium phosphide. Calcium is +2. Phosphide is -3. Now, we've got +2 and -3, and those don't neatly cancel out. If we had an extra +1, that would help, but we don't. We've only got calcium, which only comes in +2, and phosphorus only comes in -3. So the way to think about this one is to think about lowest common multiple. What is the lowest common multiple that 2 and 3 have in common? Well, it'll be 6, right? So 6 can be divided by 2. It can also be divided by 3. So we're going to have 6 positive charges and 6 negative charges to make this a neutral compound. So how do you get 6 positive charges with calcium? You have 3 of those because it's +2. And how do you get 6 negative charges with your phosphorus? You need 2 of those. So this will be Ca3P2. So that's how you write formulas for ionic compounds. Let's do a couple more here on the board. So we've already looked at these earlier, but let's go ahead and see if we can get the answers for them. So here we have lithium nitride. Now remember again, when you're looking at problems like this, you should write the 2 ions, the cation and the anion. So we're going to look up lithium, and I've got my periodic table over here. Lithium is here in group 1, so it's a +1. And nitride is all the way over here, it's a -3. So then we're going to say, okay, how many lithium atoms do I need to cancel out one nitrogen atom? Or how many nitrogens do I need to cancel out a lithium? Well, this is a -3, so I need 3 of this. So this is going to be Li3N. And that's the formula for lithium nitride. On this one, we're just writing the name. The names, of course, are really simple for ionic compounds. We're going to write the name of the cation, which is K is potassium. And then we're going to write sulfur, but we change the ending to "ide." Sometimes kids will write sulfuride. I wouldn't necessarily mark that wrong. It's technically sulfide. Sometimes it's a little tricky to figure out where to cut the word off and add the "ide" ending, but that's not too bad. So potassium sulfide is K2S. And then we have magnesium oxide. Again, since we are writing a binary ionic compound formula, we need to write the 2 ions first so we can figure out the answer. Magnesium is here in the +2 column. And of course, oxygen is over here. It's in the -2. So a +2 and a -2, how many of each? What's the minimum number of each that we need for that to cancel out? Well, that's going to cancel out already. So our correct answer here is going to be MgO. Sometimes you'll see people write Mg2O2. That's not technically correct because that's not as reduced as you could get it. So this would not be an acceptable answer. This would be correct, MgO.